All right, so let's do some review. I didn't have a chance to write all of it up yet, so we still have some more to write up, which we'll get to in a second. So, of course, we have all our rules for derivatives. Derivative of constant is 0, power of x to the a xa minus 1. Derivative of sine is cosine. Derivative of cosine is negative sine. Derivative of tangent is secant squared. Derivative of secant is secant tangent. Derivative of arctangent is 1 over 1 plus x squared. Hopefully, these will all be ingrained in your soul so that next quarter you will have no problem recalling these rules, because these will be very important as you go on in your future calculus career. Also very important, the product rule. When I have the derivative of f times g, f prime g plus fg prime. Derivative of g, which is the chain rule, f prime of g times g prime. So these are all things which I expect you to know for the second midterm, even though most of this, even though these three facts came from the first midterm, I still expect you to know them for the second midterm. Otherwise, I'd be in trouble. Now, what did we talk about last time? So 2 times back, we talked about global max and global min. And we talked about how to find them. And last time we talked about, well, how do you find the local max and local min? So recall, what does we mean by local and what do we mean by max and min? Well, max and min, that's pretty intuitive. Max, it means you're larger than everything else. Min means you're smaller than everything else. Local just means nearby. So when I'm looking for local max and local min, I'm just saying at nearby this point, I'm as large as everything I'm close to. I don't care what happens far away. So picture-wise, this point would be a local max, because if I look at it nearby, if I just narrow my focus and look at it nearby what's happening, I see it's bigger than everything else. But far away, it's not a global max. I mean, far away, there's something bigger than it. But that's okay. I only care about what's happening nearby. That's the idea of local. Now, we saw that they occur at critical points, or if we have a boundary, they occur at boundary. And usually, if you have a boundary, it always occurs at a boundary. You just have to figure out whether it's a max or a min. And recall what we mean by a critical point. It's where the derivative is equal to 0, or the derivative is undefined. Now, why do they occur at critical points? Well, because if we look at places where we are not at a critical point, then either one or two things is happening. The derivative is positive, or the derivative is negative. I mean, there's not really that many choices left. But we know something. We know if our derivative is positive, that our function is increasing. Well, if our function is increasing, we can't be at a max. So what it's telling us, if our function is increasing, means it's going uphill. So I can't be at the top. And I can't be at the minimum because if I go to the left, I'm going downhill. Similarly, if our derivative is negative, our function is decreasing. And again, if I'm at a point where my function is decreasing, so my function is doing something like this, I can't be at a max, because if I go left, I go bigger. And I can't be at a min, because if I go left, if I go right, I go smaller. So that's our intuition. That's why our max and mins, they have to occur at these critical points. Now, these are actually very nice facts to know, where the derivative is positive or increasing and where it's negative or decreasing. So we know where to look for local max and local min. Critical points. But just because I have a critical point, just having the point and even having the value of the function at that point, I don't have enough yet to figure out, is it a max or is it a min? Or maybe it's neither a max nor a min. Because we already saw an example of a function we call x cubed, where I have a critical point at 0, but it's not a max or a min. So the first derivative test takes your critical point and it tells you what kind of critical point it is. So let's say A is our critical point. And the way we think about it is, think of this as being all the numbers here. We represent it as a line. Some classes, they call this the real number line. I mark A. And what I'm going to do is I'm going to look at the derivative on the left and on the right around A. And I'm going to use what's happening with the derivative to tell me what's happening with the function. And once I know what's happening with the function, I can get an intuition about whether I'm at a max or a min or neither. So for instance, if my derivative is positive on the left-hand side of A, and it's negative on the right-hand side of A, what's happening? Well, what's happening is, to the left, I'm increasing, so I'm coming up. I hit my point A, f of A, whatever it is. And then it's decreasing and I'm going down. So this is like a really lousy graph of the function. We'll get it better at drawing functions, by the way. That'll be a lecture for next week. But right now, here we have a really lousy graph of the function. I just need to see intuition what's going on. I'm going up, and then I go down. So at the top, I'm seeing, like I said, I'm at the top. So it's the maximum. Similarly, if my derivative is negative to the left, and it's positive to the right, well, I'm first going down, because I have negative derivative. I hit my point a, f of a. Then I'm going up, because I have positive derivative. So again, this is like a really bad drawing of the function. We'll get better. Don't worry. It's exciting. Do it on Monday, I think. So we can see what's happening is at the point a, f of a, we're at the bottom. So we're at a minimum. Now there's two other possibilities, and that is if my derivative is negative on both the left and the right, in which case I'm coming down, I stop, and I go down again. Or it could be positive on both the left and the right, in which case I'm coming up, I stop, and I go up again. And it's easy to see from these pictures where I'm not at a max or a min, because again, I'm not at a max because I could go further to the left, and I'm going up. I'm increasing my value. And I'm not at a min because I could go further to the right. I'm decreasing value. Same reasoning goes here. So where the derivative doesn't change sign, we are at neither max nor min. And so how do we apply this to our problems? Well, what we do is we find the critical points, and then we're going to have some line, and we mark our critical points, whatever they happen to be, as you would like in a real number system. So it might be -5, 1, 3, 7. You know, put them in increasing order. And then what we do is we test. Now, one of the things we saw last time is that if I look at the intervals here, so there's 1, 2, 3, 4, 5 intervals. If I look at the intervals, each one of these 5 intervals, the derivative has the exact same behavior as far as being positive or negative on the entire interval. So what I want to do is I just test to see whether the derivative is positive or negative. And to test, I just pick a point. So for instance, from 1 to 3, I could pick a point. Now, pick any point you want. The goal is you should pick a point that you understand, that you can actually say something about. So maybe 2 is a nice point because 2 is a whole number. So what I would do is I would take my point 2, and I'd look at the derivative, f prime of 2. Now, I haven't said anything about the function, so let's just say it's negative. Maybe it's -7. Now, do I care about the 7? No. I don't care about the 7. I only care about the fact that it's negative, that it's less than 0. So that tells me over this range from 1 to 3, my derivative is negative, my function is decreasing. So I'd go through and I do that for each one. I'd pick a point from -5 to 1, and I see whether it's positive or negative. So let's suppose here my derivative is positive. Suppose here, again, my derivative is positive. My derivative is negative, and my derivative is positive. So what we're going to do is we go through, we test, and we're going to have all this information. And now we just go through and look at the critical points. And we say, okay, -5. My derivative was positive, and then went positive. So it's a neither case, because I'm going up, then up again. All right. How about 1? Positive, then negative. That means I'm going up, then I'm coming down. Okay, so that says 1 is a max. How about 3? Negative, then negative. Okay, that's neither. I'm going down, then I keep going down. 7? Well, I'm negative, then positive. So I'm going down, then going up. So 7 would be a min. And one other thing we can get from this picture, once we've put so much effort into getting this far, we might as well get as much as we can out of it. So one other thing we can get from this picture is we can say, where is the function increasing? So what I do is I look and say, well, okay, what's the intervals where the derivative is positive? That's where the function is increasing. So I say, okay, all right, starting from -3, I'm positive, positive, positive. I'm 0, but I still go back to being positive, so I'll pretty much ignore this -5 and say, aha, I really am positive, or at least greater than or equal to 0, all the way up to this point. So I'm increasing on this interval from -infinity up to 1. Where am I decreasing? Well, okay, it's where the derivative is negative. So again, I'm starting at 1. I see my derivative is negative. I'm going decreasing, decreasing. Here, I'm still decreasing from 3 to 7. Then after 7, I'm increasing again. So I'm going to stop at 7. And I say, aha, my function is decreasing from 1 to 7. And then finally, I see I'm increasing again because my derivative is positive, so I'm back to increasing. So even though we did this to really find the critical points and to classify them, we can also talk about where our function is increasing and decreasing. So let's work through an example. So suppose I have the function f of x is tangent of x minus 4x on the interval negative pi halves to pi halves. Now this notation here is the same as saying negative pi halves is less than x is less than pi halves. So I'm not including the pi halves. So even though I'm restricting where I'm considering my function, these aren't boundary points. Boundary points are where you have a less than or equal to sign. So I don't have boundary points to worry about here. Okay, so I'm between negative pi halves and pi halves. And it makes sense to restrict myself between negative pi halves and pi halves. Why? What do we know about tangent? Well, tangent has these asymptotes. And where are the asymptotes? Well, there's one at negative pi halves. There's one at pi halves. So by restricting myself to go between negative pi halves and pi halves, I now have a nice function. I don't have any of these vertical asymptotes. In fact, it's continuous. Okay, so if I'm looking for max and min, what's our first step? The derivative. It's always going to be the derivative because we're going to do two things. We have to find out where they are, and those are going to be critical points, and that's figured out by looking at the derivative. And we have to find out what they are. Now, we have a first derivative test. And so to use the test, we have to use the derivative. Okay, so I start by taking the derivative. The derivative of this, well, the derivative of tangent. Lo and behold, we wrote it down, so that's good. Secant squared x and the derivative of 4x will be simply 4. So I have the derivative of my function is secant squared x minus 4. So the first thing we checked, is there any place where the derivative is undefined? Because that's a critical point, which well, it's kind of underneath here, but it says it right there. If you had X-ray vision, you'd see undefined. All right. Is this function ever undefined? Well, certainly secant is undefined, but remember, I only care about what's happening in this interval between negative pi halves and pi halves. And between negative pi halves and pi halves, secant is hunky-dory. He's a happy camper. Okay, so I don't have any problems with being undefined. So what's the next thing I do? I set it equal to 0. So that's finding my other kind of critical point, which is the most common kind that we encounter. So we saw secant squared x minus 4 equals 0. So we just start playing around with this. Secant squared x is equal to 4. Now secant squared, secant is 1 over cosine. So this is the same as 1 over cosine squared. And now we just do some switching. If I rearrange this, this is the same as saying cosine squared x equals 1/4. One way to see it is you just imagine flipping both sides. Cosine squared x is 1/4. Okay? So if that's cosine squared x, then we get cosine of x is plus or minus the square root of 1/4, or that's plus or minus 1/2. Okay, so now I'm looking for when does cosine equal plus or minus 1/2. And again, I don't care about all the values. I only care about the values between negative pi halves and pi halves. Because actually, cosine is this infinitely repeating function. So there's infinitely many points where this is true. But I just want the ones between negative pi halves and pi halves. So does anybody remember when does cosine equal plus 1/2? Yeah. So this happens at x equals pi over 3. Anywhere else? Yeah, negative pi over 3. Because you might remember that one of the things we mentioned a while back is that cosine is what's called an even function. So that says cosine of negative x is the same as saying as cosine of positive x. So the cosine of negative pi thirds is the same as cosine of pi thirds. Now these are when the cosine equals 1/2. When does cosine equal negative 1/2? Well, cosine equals negative 1/2 at 2 pi thirds. And so we negative 2 pi thirds. Now, why don't we care about those? Yeah, they're out. 2 pi thirds It's bigger than pi halves. If you don't see that, just think 1/2 and 2/3. 1/2 is smaller than 2/3. So in fact, these are my only two critical points. Okay, so that's x equals pi thirds and minus pi thirds. Now this tells us where to look. Now we need to classify them. Now, how do we classify them? Well, we can use our first derivative test. So I have my point negative pi thirds, and I have my point pi thirds. And really, my universe stops at negative pi halves and positive pi halves. So I really only care what's happening in here. So I don't want to plug in something like negative pi, because I'm only considering between negative pi halves and pi halves. Okay, well, let's pick something simple. How about, is there a number between negative pi thirds and pi thirds that's easy for us to figure out? 0, yeah. Okay, let me use a different color so I don't confuse them. So I'm going to take 0. I plug it in. F prime of 0. Well, secant of 0 is 1. 1 squared is 1. Minus 4 is negative 3. So this tells me that between negative pi thirds and pi thirds, my derivative is negative. So I'm decreasing. Okay, now the real trick. How about between negative pi thirds and negative pi halves, or if you like, between pi thirds and pi halves? Now it's not so clear. Well, what's an angle between pi thirds and pi halves? That we know. There's a lot of angles between them, but we don't know them. So let's think about it. Let's see if we can avoid that. Let's come back to our derivative. So we said f prime of x is secant squared x minus 4. Do we know what the graph of secant squared x looks like? Yeah, secant squared x looks a lot like a u. I'm really stretching back to see if you remember your trigonometry days here. If I take secant squared x and subtract 4, what do I do to that graph? I move it down. Yeah, moving it down. Exactly. So if that's secant squared x minus 4 looks something like this. And in fact, there's asymptotes at negative pi halves and pi halves here. And we found this pi thirds is one place where we hit 0, and negative pi thirds is another place where we hit 0. Okay, and now here's a graph of the derivative. So instead of trying to plug in a value, I can just, if I understand the derivative, that's really what I need. I just need to see is the derivative positive or negative. Now here, we already saw that when we plugged in 0, we got negative, which is good. That matches with the picture. What about these two places? What's happening with the derivative? Yeah, the value of the derivative is positive. This is not, remember, this is the graph of f prime, not the graph of f. So that says f prime is, let me write underneath, f prime is greater than 0, and f prime is greater than 0. Okay. Now we're ready to read off what's happening. What can you tell me about negative pi thirds? Yeah, I'm coming up, then I'm going down. So pi thirds is a max. How about, sorry, negative pi thirds is the max. How about pi thirds? It's a minimum because I'm coming down, I'm at pi thirds, and I'm going up. Now here we have to be a little bit careful with the terminology, because sometimes questions will say, find max or min, and they might be asking for one or two things. They might be saying, find the x values for where the max and min occur, and in that case, we'd be done. So at x equals negative pi thirds, we're at a min, and at x equals, max, excuse me. And at x equals pi thirds, we're at a min. So if it asks us for where max and min occur, we just need to find the x values and classify them, and we're done. But it might say, what is the maximum value? Now, as soon as you see the word value, what do you have to do? Yeah, you have to plug these points, these x values, back in. Into what function? Into the original function, not into the derivative, because we want to talk about the maximum value of the function. So we plug it back in here. So for instance, we saw negative pi thirds was a max, and what is that value? Well, we plug it in. F of negative pi thirds is tangent of negative pi thirds minus 4 times negative pi thirds. And we think about, okay, what's tangent of negative pi thirds? It's negative root 3. And then plus 4 pi over 3. So the max happens at negative pi thirds, and the maximum value is negative root 3 plus 4 pi thirds. The min happens at pi thirds, and what's the minimum value there? Well, we plug it in. Tangent of pi thirds minus 4 times pi thirds, which turns out to be root 3 minus 4 pi thirds. Okay, so this is an example of the stuff we did last time. Okay, good. So just remember, if it asks for location, x values, if it asks for values, find the x values and then go one more step further and plug it back into the original function. Now, there's one thing we mentioned at the end of the class last time. Which is Rolle's theorem and the mean value theorem. So let me write these down again. So Rolle's theorem says the following: f continuous on the interval a less than or equal to x less than or equal to b, and f is differentiable. In other words, whenever you see the word differentiable, it just means you can take a derivative on a less than x less than b. We don't care about what happens at the endpoints. And one more thing, f of a equals f of b. These three facts combined tell us there is a c, which is between a and b. That is a less than c less than b, so that the derivative evaluated at c is 0. And we saw a proof of this. The intuition is, okay, if we have a continuous function on an interval from a to b, it has a max or a min. Now, one of two things happens. Either it's constant, in which case every point has a derivative equal to 0. Notice here that I say there is a c, but there could in fact be many c, and possibly infinitely many values c where this is true. I'm just saying there's at least one. There could be 2, 3, 5, 100, but there's at least one. Okay, so it's continuous, so it has a max or min. Max or min occurs at a critical point. What is a critical point? It's where the derivative is 0 or undefined, but it can't be undefined because of our assumption here. So that's where the derivative is 0. So that was the intuition. Now, there's another theorem that looks really close to this, which is called the mean value theorem. Now, here, mean doesn't mean like cruel. It means like the average. Much like people want to ask, what was the mean on the test? You know, that's the kind of mean we're talking about. And it has some similar assumption. F is continuous on some interval between a and b, a less than x less than or equal to b. And f is differentiable on a less than x less than b. Now, these are my two assumptions. What can we conclude? Well, again, some c with c between a and b, so a less than c less than b, where f prime of c is equal to f of b minus f of a divided by b minus a. Okay, that's the mean value theorem. Now, we mentioned these together because they look really, really similar to one another. Notice that these conditions, two conditions here, match. It turns out that they're essentially the same fact. Let's see it. How do I start with the mean value theorem and get Rolle's theorem? Well, suppose I have a function which is continuous and differentiable, and suppose f of a equals f of b. What happens when I put f of a equals f of b into this? I get 0 on the top. So if f of a equals f of b, it says there's some c between a and b where f prime of c equals 0. That's exactly what I have over here. That's Rolle's theorem. Now, how do we get from Rolle's theorem to the mean value theorem? Well, that one we use a little bit of a trick. We say, well, we can do that. We have our ways. What we do is I just say, well, look at this function. I'll call it g of x. And the function is very simple. It's f of x minus f of a. So f of a, remember, is a number. X is the variable. Everything else is a number. Times b minus a minus f of b minus f of a times x minus a. Now, if f is a continuous function, then g is a continuous function. Because this is continuous. If I subtract a constant, it's continuous. If I multiply by a constant, it's continuous. This is a line. It's a constant times x minus a constant. If I combine two continuous functions, it's continuous. So g of x is continuous. But it's not only continuous, it's still differentiable. As long as I can take a derivative of f, I can take a derivative of g. So that means I satisfy these first two conditions. It's continuous and it's differentiable. What is g of a? Well, when I plug a, what happens to this piece? It becomes 0. F of a minus f of a is 0. What happens to this piece? It becomes 0. A minus a is 0. So g evaluated at a is 0. What is g evaluated at b? Well, I get f of b minus f of a times b minus a minus f of b minus f of a times b minus a, which is 0 again. Now, the important thing is that these are equal to one another. So since they're equal, that satisfies the last condition. So I have a continuous function, which is differentiable, and the endpoints agree. So this implies that there is some c with g prime of c equal to 0, where c is between a and b. Now, okay, good. So far so good. What's the derivative of g prime? Well, the derivative of this, derivative of f of a is 0. It's just a constant. So it's f prime of x times b minus a. That's the derivative of the first piece. What's the derivative of this piece? Well, simply it's this constant times derivative of x minus a. Derivative of x minus a is 1. So it's simply the constant, f of b minus f of a. And now g prime of c equals 0 says, okay, g prime of c is f prime of c times b minus a minus f of b minus f of a. All this is equal to 0. So I start using some of my chalkboard sophisticated technology here. Move this to the other side. That becomes an equals. Divide both sides by b minus a. And lo and behold, g prime of c being 0 is the same as saying f prime of c is f of b minus f of a over b minus a, which is exactly what I was trying to show here. So these are equivalent statements. So since we know Rolle's theorem is true, that means we automatically know the mean value theorem is true. Now, we talked about the mean value theorem a little bit last time. This is talking about the average rate of change. In other words, we start at a f of a, we go to b f of b. What was the average rate we changed? So analogy is driving a car. It's very intuitive. So I start in San Diego. I end up in Los Angeles. It takes 2 hours. It's a 120-mile trip. So the difference in my position is 120 miles. The difference in time is 2 hours. So it would be like 60 miles per hour. F prime of c says there's an instantaneous rate of change. I'll abbreviate rate of change here. So again, going back to driving speed, this says if I average 60 miles per hour, then at some point in time, I had to be going at exactly 60 miles per hour. So in other words, I can't get between San Diego and Los Angeles in 2 hours and not be going whatever the average speed was. Cops can use this. If they don't want to use radar, if they have two landmarks they know are a fixed distance apart, and they know how long it takes to go if you're driving the legal speed limit, they can just take a stopwatch. And they start when you go past the first object, they stop when you go past the second, and they look at the time. They don't need to use radar. They got calculus, which is better. Because they know if your average speed was faster than the speed limit, you had to be breaking the speed limit at some point. All right. Now visually, this says if I have my function, so to make it look like a function. If here is a, and here is b, f of b minus f of a over b minus a, that's the slope of this line. In other words, it's the slope that passes through these 2 points, where this point here is a f of a, and this point here is b f of b. So what we're saying here is the slope of this line, which passes between the 2 endpoints, is equal to the slope of some point in between. So imagine if I just were to just take this line and just slowly start dragging it down. And I form these sequences of parallel lines. Eventually, I'll get to a parallel line which just touches the curve. So this has the same slope, and it's at our point C. So in other words, the derivative at this point is the same as the slope of the secant line. The slope of this tangent line equals the slope of that secant line. All right. So one of the questions you might be asked, we are spending a lot of time on this. It's okay. Concavity is fast. We'll get through it quickly. No problem. All right. Grab some chalk here. So we might be given a function f of x, x cubed minus 3x squared. And then we might be asked to do something like verify the mean value theorem. Of course, we know it's true, but let's get the check. On some interval, so let's say -1 less than or equal to x, less than or equal to 3. So what we have a function which is continuous. It's a polynomial, and it's differentiable because polynomials are very nice. They do pretty much what we want them to do. And we have an interval -1 less than or equal to x less than or equal to 3. In other words, this is a, -1, this is b, this is 3. So what we have to find is we have to see that there's some point f prime of c which is equal to f of b minus f of a over b minus a for this particular function. This is the mean value theorem, so we have to verify that this is true. All right, so let's plug in what we know. Let's plug in f of b minus f of a over b minus a. Hopefully I chose nice numbers. So f of b, that's the same as saying plug in 3. 3 cubed minus 3 times 3 squared is 0. Oh, okay, that's good. Hopefully I didn't make it too nice. All right, f of a. -1 cubed is -1. Minus 3 times -1 squared is -4. So 0 minus -4 divided by b minus a. So b is 3 minus -1. So minus minus makes plus, so 1. So according to the mean value theorem, if it's true, which it is, I'm not trying to cast doubt, it is true, there should be some point between -1 and 3, at least one, which has the derivative equal to 1. All right, what's the derivative of our function? Yeah, 3x squared minus 6x. So we need to find f prime of c, which is 3c squared minus 6c, so that it is equal to 1. Or 3c squared minus 6c minus 1 equals 0. As long as I can find some c which satisfies this equation and is between -1 and +3, I'm done. Now, I might find more than one, but I just need to find one. Occasionally, you might have a problem that says find all of them, in which case you find all of them. Okay, so how do we do this? Well, if you're awesome at factoring, you can probably factor this. I'm not that awesome. But we're in luck. What is this? It's quadratic. Do we have a formula for solving quadratics? A quadratic formula, if you will. And we do. We do. It tells us that c is equal to -b plus or minus the square root of b squared minus 4ac. So 4 times a, which is 3, times c, which is -1. So that becomes actually a plus 12, all divided by 2a. Now, this is 1, which is 6 over 6, plus or minus. Now, let's think about 36 plus 12. 36 plus 12 is 48. So let's just do a little scratch work up here. This is square root of 48. Now, 48 is the same as 16 times 3. So this is the same as 4 root 3. Okay, so this is the same as 4 root 3, but I divide by 6, so I get 2/3 root 3. Okay. Good? So these are our possible C values. 1 plus or minus 2/3 times the root 3. Now, we have to check, are these between -1 and +3? If they are, we're done. If not, we're in trouble. Now, they might both be between them, or just one of them might be between them. Of course, the problem here is, what is root 3? Let's say root 3 is roughly around, what, 1.8? It's less than 2. Certainly less than 2. So 1 plus 4/3 is bigger than 1, which is bigger than -1, but it's less than 3. And certainly 1 minus 4/3 is bigger than -1. And it's between 3. So in fact, it turns out, in this case, we had 2 values. Both of them fit the range. Now, usually on a test, we won't have you have to figure out square roots. In this case, it turns out it's true, and here are 2 values that satisfy the relationship. Now, one more thing about the mean value theorem. There's a fun fact. Where's my eraser? Oh, there it is. Okay. This is a useful thing to know. We'll make use of it in a few weeks. So we should state it here. So this is what we call well, we have the mean value theorem. So there's a fact that it follows from the theorem. Now, if we were teaching this class in the US, we would pronounce this word corollary. And that's because we don't know how to speak English. If we were teaching this class over in England, then we would be pronouncing the word correctly, and we would be saying corollary. I learned this because I had a professor from England, and every time he said corollary, I was just like made my day. It was great. There's a rule. You count back from the end, 3, and that's where you put your emphasis on. So it's not on the core, it's on the roll. Corollary. Okay, so the corollary is the following. If f prime of x is 0, you do that to make the rest of the chalk nervous. Then they know they're in trouble if they make any more noise. Then f of x is constant. So in other words, if I have a derivative of a function and it's 0, I know what the function was. It was a constant function. This is pretty intuitive. We say, well, yeah, don't we know that already? Well, we kind of know the opposite. We know that if our function is constant, then the derivative is 0. This is saying that the opposite is also true. If the derivative is 0, the function it came from was a constant. We would call this a converse using our mathematical parlance. Now, how do we prove that? Well, very simple. Let's just fix a value. All right. So pick any a and b. If I can show that f of a has to equal f of b, I'm done, no matter which a and b I pick. Because if f of a equals f of b, and f of a equals f of c, then by transitivity, they all equal one another. So pick any a and b. By the mean value theorem, I know that f of b minus f of a over b minus a is equal to the derivative at some point between a and b. Now here's my trick. What do I know about this? My derivative is 0. So I'm not talking about my derivative at a point. I'm talking about the derivative at every point is 0. So this is 0. So that implies f of b minus f of a is 0. Or that implies that f of b equals f of a. So I pick any 2 points, I get the exact same value. The only function that does that is a constant function. All right, I really want to do one example. I know this will get us a little bit behind, but here's a fun problem. Okay, suppose you have 2 functions, f of x and g of x, And they satisfy the following 3 facts. First fact is that f prime of x is equal to g. Actually, we'll say 4 facts. The derivative of f is g. Second fact, the derivative of g is f. The next fact, f of 0 is 1. And the last fact is g of 0 is 0. Suppose I tell you I have 2 functions satisfying the following 4 facts. Here's my question. What is f of 100 squared minus g of 100 squared? Now, at first glance, it seems like, oh, come on, you're pulling my leg. Because you already told us that this is really only telling us information about 0. How in the world can I tell you anything about what's happening over at 100? This doesn't seem like a fair question. And I'm saying, no, you can answer this question. And you're like, really? There must be a trick here. Let's think about it. What's our trick? Well, let's write a function. Let's call it h of x. Let's call it f of x quantity squared minus g of x quantity squared. What is h prime of x? So we use the chain rule. 2 times the function raised to the first power times f prime of x minus 2 times the function raised to the first power times g prime of x. That's the chain rule. Now, what fact can I use here? Well, I can use the fact my derivative of f is equal to g. And I can use the fact my derivative of g is equal to f. So this is equal to 2 times f of x times g of x minus 2 times g of x times f of x. And what is this equal to? It's equal to 0. What does that tell me about my function h? It's a constant function. So the value of the function h at 100, which is what I'm trying to find, is the same as the value of h at, I don't know, 0? Because I know what h of 0 is. H of 0 is f of 0 squared minus g of 0 squared. But f of 0 is 1. G of 0 is 0. So the value of the function at 0 is 1. But as we said, this is a constant. So this is all equal to 1. By the way, are there 2 functions that do this, you might wonder? There are. You haven't seen these functions before. You won't be tested on them. But there are functions called cosh and sinh. Well, the nickname for them is cosh, because it's spelled C-O-S-H. This stands for the hyperbolic cosine. And this is e to the x plus e to the minus x divided by 2. And this is e to the x minus e to the minus x divided by 2. And we haven't talked about these exponential functions, which is why we haven't defined these functions before. You might wonder, why do we call them cosh and sinh? Well, they basically behave just like cosine and sine. So for example, sinh of 2x is 2 sinh x cosh x. And pretty much every single trig identity has a translate over into these hyperbolic identities. Now, I will say, you may not have seen cosh as a function before, but you've seen pictures of it all your life, and you never realized it. That is because if you ever saw anything like the Golden Gate Bridge, or any time you saw a rope hanging between 2 poles, you looked at the rope and it forms a shape. Now, depending upon what algebra book you read, what shape were you told this is? Parabola. That's all a filthy lie. It's not a parabola. It's this function. It's a cosh function. I think it's called a catenary. Okay, so in the last 3 minutes, let's talk about the second derivative. So we have a first derivative test, And we need a second derivative test. And we're going to get the second derivative test on Monday. That'll be pretty much the first thing we do right off the bat. But before we talk about the second derivative test, we really need to talk about what is the second derivative measuring. So the second derivative tells us what? Well, recall the second derivative is the derivative of the first derivative. So if the first derivative tells us how the function is changing, how it's increasing or decreasing, the second derivative tells us how the first derivative is changing, whether it's increasing or decreasing. And as far as the function goes, the second derivative measures something about concavity. Now, the book had a nice word for this. Concavity is like how the function is bending. So in other words, is my function, is it bending upward? Is it bending downward? So what do I mean? Well, so bending upward is something like this, where I have a shape where I do this, or maybe it might look like this, or maybe it might look like this. The point here is I think about my slopes. My slopes are going from very large negative to small negative to 0 to large positive. In this case, it starts off as a small positive, gets larger and larger. So these are bending up, which we call this concave up. Similarly, we could be going down, bending down. Would be shapes that look like this, or they might look like this, or they might look like this. So these are bending downward. Sorry. So that means concave down. And one of the things that we saw a few weeks ago were that these basic behaviors are determined by the second derivative. So you might recall that we talked about this already, where here we saw the second derivative tells us that our slopes were coming from large negative to 0 to large positive. So our slopes were going up. They were increasing. Here, our slopes were coming from a large positive, getting smaller and smaller to 0, and then getting larger and larger negative. And so here's the trick. Bending up, concave up, is the same as saying, let me erase the picture here, f prime of x is increasing. Our slopes are getting larger and larger positively. Concave down is the same as saying f prime of x is decreasing. And now we use our fact. What does it mean for a function to be increasing? The function is increasing where our derivative is positive. We said it over here. Our function is increasing where the derivative is positive. So if I want my function f prime to be increasing, that tells me my f double prime is positive. Now, where is it decreasing? It's where the derivative is negative. So the derivative of f prime is f double prime. So the derivative is negative. So concave down, derivative is negative. Concave up, derivative is positive. Let's stop there. We'll pick it up on Monday. Don't forget to turn your homework in before you go. And have a good weekend. Woo!